While the ice core record we discussed in the last lecture is clearly physically restricted to the polar regions, features correlated with ice core changes are found at all latitudes. From caves in China, where we can measure isotopic shifts in the rainfall in stalactites, to ocean floor sediments off New Zealand, we see that there are global changes whenever we see changes in the ice core reflecting temperature fluctuations, wind speed fluctuations, and precipitation changes. However, we know that regional changes are large and are not necessarily the same everywhere in the world. Changes in temperature and precipitation accompany global climate shifts, and having measurements that we can make in the 95% of the world that's not covered by ice is important to understanding these effects. Coral reefs and seafloor sediments provide a record that charts the synchronous rise and fall of the sea with the ice ages, as well as allowing us to probe much further back in time and to explore these regional climatic effects. To produce the massive glaciers of ice that the ice ages see means a very large volume of water must be transferred to the land. And this large volume of water can only come from one place, the oceans. How do we know how large the glaciers are? They leave scars on the land which the astute observer can easily see. In my class at Columbia, I take my students out to Central Park, where there are several massive outcroppings of bedrock called Manhattan schist, appropriately enough. In this bedrock, one can see deep grooves, about this wide and sometimes that deep, that run in parallel over these large outcroppings of the rock. What this represents is a place where the last glacier, which only 20,000 years ago was more than a mile thick over Manhattan, has slowly and inexorably dragged large boulders with it and scoured out streaks in these rocks. Some of the boulders are actually left behind. These rocks are called erratics. They're erratic because they don't belong to the geology of the region, but have been carried hundreds, perhaps even thousands of miles from their origin, and then dumped there when the glacier retreats. In addition, large geographic features are a consequence of the glacier's advance. Long Island, for example, the 100-mile-long island that exists off Manhattan, is actually a glacial moraine, a place where the glacier, acting like a bulldozer, stopped in the last ice age, and as it retreated and melted back, left a pile of detritus, a pile big enough that it's 10 miles wide and 100 miles long and hundreds of meters deep, that makes up Long Island today. So we have good geological markers for the size and extent of the glaciers during the glacial maximum. Coral reefs, in addition to helping us calibrate the carbon-14 clock, as we discussed last time, provide an excellent prehistoric tidal gauge, if you will, that allows us to read the history of past sea levels and decide whether or not how much water from the ocean ended up on the land. We can make a rough estimate of this from the geological features I described earlier. It looks as though the glaciers advanced nearly 4,000 kilometers down from the pole, and if you take the average circumference of the Earth at these latitudes of about 7,000 kilometers and recognize the glaciers were about 2 kilometers thick, that means a total of about 5.6 times 10 to the 7th, or 56 million cubic kilometers of ice. Now, if you imagine taking that from the oceans, taking the whole area of the ocean, which is about 70% of the whole area of the Earth, and dividing that into that volume of ice, you find a depth of ocean that must have disappeared of 150 meters, nearly 500 feet fall in sea level, or half the height of the Empire State Building. This is our crude estimate from the land area and the thickness of the glaciers that we think must have existed during the ice ages. Corals can help us measure this in quantitative detail. Corals are animals, actually, a few millimeters in size, that live in a complex relationship with the marine ecosystem. They exist in colonies of thousands to millions of identical individuals called polyps that can reproduce both asexually by splitting and sexually by releasing gametes into the water. Well, these creatures have little tiny stinging tentacles with which they can catch plankton and microscopic fish and other little sea creatures. Most of their nutrition from a large collection of coral comes from symbiotic photosynthesizing algae, That is, algae that lives in a relationship with the polyps and uses photosynthesis to produce food. The principal signature of coral, of course, the thing you think of in your mind when I say that word, are the massive and beautiful reefs that are formed, built up over thousands of generations of coral as they secrete calcium carbonate, the material that makes shells. Because of the algae that the coral need to live with, coral can only live between 5 and 50 meters below the ocean surface. 50 meters being the maximum depth to which enough sunlight penetrates that photosynthesis in these algae can occur. In addition, depending on the species, they require certain temperature and salinity conditions to thrive. If the sea level suddenly falls, a coral reef is left exposed, and then it dies. If the sea level suddenly rises, the reef drowns because insufficient sunlight can reach the photosynthetic algae that the coral polyps rely on for their growth. Radioactive dating using both carbon-14, because the coral are living creatures and therefore suck carbon out of the water, and the uranium-234, thorium-230 clock that we talked about earlier, allow us to date the changes in the rise and fall of sea level in coral reefs precisely. As but one example, a sudden sea level rise of about 15 to 20 meters, that's 60 or 70 feet, in less than 500 years, has been identified from Tahitian coral reefs as occurring about 14,700 years ago, just as the world began the transition out of the last ice age towards the current interglacial period in which we reside. Detailed analysis of many reefs off Barbados, the same ones that my Columbia colleagues used for dating before that corrected the carbon-14 dates back 50,000 years, allow us to determine the time of the last glacial maximum, that is, the glacial maximum being when the sea level was lowest, about 21,000 to 26,000 years before the present, with a total sea level fall very close to that crude calculation I gave you of about 130 meters, or over 400 feet. The coastlines of the world look very different during an ice age because so much of the ocean water ends up on land. Even more sudden rises of 3 and 4 meters heights have been inferred during the last interglacial period, 125,000 years ago, the last time the world was relatively free of ice as it is today, when sea levels were near today's level. Presumably, that sudden rise then was also a consequence of the collapse of an ice sheet, a large ice sheet sliding off a continent into the ocean and raising sea levels suddenly. In addition to the orbit-driven ice age cycles, the ones caused by the precession of the Earth, the changing tilt of the Earth's axis, and the changing size of the Earth's orbit that we've discussed, some researchers have claimed there's a 1,500-year oscillation of climate, and they have linked it to variability in the sun. The data come from North Atlantic ocean cores. Just as with ice, we take a drill and go down through the ice and pull out a cross-section of the ice with which we can measure the history of climate, we can do the same thing in the bottom of the ocean. Obviously, oil is drilled in the bottom of the ocean, and so we have this equipment readily set up. We can drill down and pull out a core about this big around, in which every layer going down allows us to go backwards in time. These cores in the middle of the North Atlantic Ocean reveal in alternating bands little grains of reddish rock. It doesn't bear any geological resemblance to the other materials in that part of the ocean floor, but indeed, chemically and isotopically, it's identical in composition to rocks that are on the surface of northern Canada and parts of Greenland. These little reddish grains from thousands of kilometers away are thought to be delivered to the mid-Atlantic by huge flotillas of icebergs breaking off the Canadian and the Greenland glaciers and drifting south, far enough south to drop their grains off the bottom as the icebergs melt, to leave these grains in a location where they're geologically foreign. This requires, for the icebergs to get this far south, significantly colder ocean temperatures during these periods. These layers of red grains recur with a period of 1,500 years. 9 different such layers have been identified in the last 12,000 years since the rough end of the last ice age. These same authors have identified simultaneously an increase in the formation rate of carbon-14 and another radioactive isotope produced in the atmosphere, beryllium-10, both of which come about as a consequence of these high-energy particles striking nitrogen and oxygen atoms in the atmosphere of Earth. Now, as I mentioned earlier, when the sun is active, that is, when its energy output is high and there's lots of sunspots on the surface, its overall global magnetic field extends out and embraces the Earth, helping to shield it from these cosmic rays coming in, meaning that the rate of production of these radioactive isotopes, like carbon and beryllium, goes down. What these authors that identified the 1,500-year cycle of red grain deposit in the middle of the Atlantic have shown, in that when those red grains are deposited, the amount of carbon-14 and beryllium-10 actually increases, suggesting that the sun is in a less active phase, having withdrawn its magnetic field, removed the protective blanket from Earth, and allowed the cosmic rays to generate more of these elements. The suggestion that the sun undergoes a roughly periodic change in activity levels that influence Earth's climate significantly on millennial timescales is a little controversial. As we shall see when we study the stars, there is nothing in the life cycle of a star that suggests such short periods of fluctuation. Indeed, changes in stars tend to be measured in millions to billions of years, not just thousands of years. So personally, I remain somewhat skeptical that changes in solar output is a consequence of changes in solar output actually produce these changes in sea surface temperature. But there's compelling evidence that sea surface temperature actually does change. Analysis of ocean cores from West Africa, thousands of kilometers from the red grain deposits in the North Atlantic, show additional indications of temperature change that are correlated with the grain deposition. The mix of species of tiny single-celled planktonic organism that are called foraminifera, or forams for short, are extremely sensitive to sea surface temperature. Changing the temperature of the surface by a couple of degrees changes completely the mix of species of these forams that one can detect. Now, the forams are ideal climate tracers because they form little calciferous shells, just like little clam shells, only they're much, much tinier. And as they die, they sink to the bottom of the ocean and, year after year, produce layers which allow one to, again, have a record of climate change. Each species have a different kind of shell. Some of them curve left, some of them curve right, some of them have lots of holes, some of them are more solid. And a trained eye, I must confess I don't have one of those, but a trained eye can easily detect which kind of species it is under a microscope looking at the shells of these forams. Now, one can also take these shells and analyze them isotopically, as we're now familiar with doing. And the oxygen isotope ratios incorporated into these shells provide a direct measure of sea surface temperature as well. Recall how the heavy oxygen, oxygen 18, when combined with hydrogen, makes H218O, heavy water. And the heavy molecules, as always, move more slowly than the light ones. Thus, as we found in the ice, when temperatures rise, the heavy molecules tend to escape the sea more readily and fall in rain on the ice, meaning an excess of heavy isotopes corresponds to a high temperature in the ice cores. But the exact opposite effect, of course, must be found in these shells, because if the heavy oxygen is evaporating with the water into the atmosphere, that leaves less of it in the ocean for it to be incorporated into the shells of these creatures. So we have the exact opposite effect. On warm temperatures, there's a smaller amount of H2O18, or O18, found in these seashells, and for low temperatures, there's an excess of O18. Thus, isotopic analysis of these shells allows us to measure the temperature with reasonable precision. Drops in equatorial sea surface temperature are correlated with the ice-rafted debris in the North Atlantic several thousand kilometers away off Africa. These cores off West Africa also reveal much larger quantities of Sahara desert dust blown off the continent in the cold periods, indicating that it was drier then. You may have seen satellite photographs of these plumes of dust that are blown off the Sahara today. They're really quite extraordinary. They reach all the way from Africa to the Caribbean and to Florida. Particles precipitating out of the atmosphere borne aloft by the winds from the desert. Now we know today, of course, the Sahara is very dry, which means these winds can carry the dust a long way. It appears also the Sahara was very dry during the periods of colder ocean surface temperatures that correspond to the red grains in the North Atlantic and extra dust deposits off Africa. In addition, this dust carries along pollen grains, which, as it settles onto the surface of the ocean, gradually rain to the bottom of the sea. By analyzing these pollen grains, we can tell whether they come from C3 plants or C4 plants, those two different photosynthetic pathways we discussed before, which discriminate against carbon-13 in different ways, the C3 plants having less carbon-13, the C4 plants having relatively more. By analyzing the C13 to C12 ratio in these pollen grains, we can calculate the fraction of C3 versus C4 plants. And, yet again, consistent with the other data, we find that during the cooler cycles, when the red grains are deposited, when the dry dust blows into the ocean, their C3 plants predominate, whereas, or C4 plants rather, predominate under the dry conditions. The cores from seabeds in the Arabian Sea, on the other side of Africa, and the Gulf of Aden also show plant species change when the red grains are present in the North Atlantic. Dust storms scrub the waxy material off the leaves of plants and carry it with the dust out to the sea. You know how plant leaves feel slightly waxy? That's an organic substance which can be rubbed off by sand grains brushing against it as the wind blows it over and attached to the sand grains, which actually ends up being a dominant component of the organic material found in the terrestrial dust in the sea-ocean cores. The carbon-13 to carbon-12 ratios in this wax also allows the determination of the relative mix between the C3 and the C4 plants. And again, the dry conditions coincide with higher C4 plant abundance. It is worth pausing here with that statement to see how far we have come. We understand that carbon, an atom which always has 6 protons and 6 electrons and therefore chemically behaves the same way, comes in different isotopes, a consequence of the different number of neutrons in its nucleus. The plants absorb the different isotopes at different rates owing to the physics of heat, which is just the motion of individual particles, of the way energy and chemical change involve a discrimination against the slower moving, heavier carbon-13 molecules. That the sea cores, by their layered nature, as with ice cores and the rings of trees, offer a calendar of past events that, opened appropriately, we can read. And that isotopic analysis of the organic matter in this wind-blown dust thousands of miles away on the sea floor reveals the mix of plant species, which in turn is controlled by the changing climate. The mix of atoms on the ocean floor tells us this whole story. The sea cores also provide a history of the tropical monsoons and demonstrate that the amount of sunlight shining on the equatorial latitudes, in addition to the orbit-driven ice cycles at the poles, is an important determinant of climate there. Monsoons are regular seasonal rainfalls. The term was first applied to India, but they occur in several parts of the world. And they result from the differential heating of the land and the ocean. Water has a high heat capacity. That is, it can soak up a lot of heat before the temperature rises very much, because a large column of water, down tens of meters, is warmed and regularly mixed. So imagine heat coming in from the sun, energy coming in from the sun. Energy comes in the form of photons, light that we can see, and is absorbed by the molecules of water in the surface of the ocean. These molecules become warmer. Again, what do we mean by warmer? We mean the molecules are jiggling faster. But the ocean is very turbulent, and so some of these rapidly moving molecules get mixed down lower in the ocean, where the molecules are moving more slowly. They collide with each other, and they share their energy equally, as all such particles do. Thus, the sunlight has to continue to shine on the ocean for a long period of time before it gets all those molecules in the contact region moving rapidly, before, in other words, the sea surface temperature will rise. On land, the molecules also absorb energy from the sun and make themselves jiggle faster, but it's only the top meter or so of soil that actually warms up in response to energy input for the sun. And so, it takes much less time to warm the land than to warm the ocean. Those of us who live on the east coast of the United States understand this in terms of our climate seasons. The warmest part of the year is in August and September, long past the point where the maximum amount of sunlight was shining on the Earth, because it takes that long to warm up the ocean around us, and the ocean exchanging energy with the air keeps it warm well into the fall. Whereas the cold part of the year comes in February, a couple of months after the minimum amount of sunlight hitting the Earth, because the ocean is still cooling off. It retains some warmth, and it takes a long time for it to lose all that energy to the cold atmosphere above it. Monsoons are an extreme response to this kind of differential heating of land areas and oceans. As the land heats, the air in contact with it, as the molecules come in and bounce off, those jiggling molecules, rise. The air rising creates a region where air from the ocean can come in. The air from the ocean, of course, is more saturated with water because it's in contact with all those water molecules, which is evaporated into the air. As they come in and rise up, in the case of India, the foothills of the Himalayas, the water condenses and falls in the form of rain. In the opposite season of the year, when the ocean is warmer than the land, the air above the ocean rises and the air from the land rushes out towards the sea. So these seasonal monsoon changes are critically important to the agriculture and all of life on the subcontinent of India. And understanding their intensity over long periods of time is important to our understanding of climate. A 120-foot-long sediment core taken off the coast of West Africa provides a continuous 155,000-year history of monsoon intensity. The age going down in the core, because the sedimentation rate is not necessarily constant, was derived from that argon 40 to argon 39 test of radioactive decay that we talked about in a few lectures ago. The oxygen 18 isotopic signature in the forams indicate that the warmer periods correspond to more intense monsoons. This is not surprising, because the warmer it is, the more energy the ocean absorbs. The more energy the ocean absorbs, the more rapidly its molecules are moving, and the more easily the most rapidly moving molecules of water can escape into the air, that is, evaporate. The more evaporation there is, the more saturated the air becomes, and when the water then condenses in the air, the more intense the rainfall. The monsoonal cycles, it turns out, are linked both to the high-latitude solar energy input, which governs the ice ages through the precession, tilt, and orbital changes of the Earth, and to the maximum amount of sunlight that's striking the equator in either March or September, the spring or the fall. This adds a certain complexity, having to take into account the tilt cycles of the Earth separately from the other orbital changes. Putting them both together leads to maximum monsoon intensity. Longer-term ocean sediment records suggest a link between changing climate and human evolution in Africa. Deep cores off both the west and east coast of Africa yield continuous records for the past 5 million years, the time over which the human species has evolved. Prior to 2.8 million years before the present, the dominant cycle was the 23,000-year axis precession of the Earth. That's when we went from warm and wet to dry and cold. Since that time, after 2.8 million years ago, first the 40,000-year tilt cycle became dominant, and then, as is true at present, as we saw in the ice cores, the 110,000-year ellipticity change cycle has become dominant, just as they do in the ice core records. Why this is so, why one cycle of Earth orbital changes dominates at one period of history and another cycle at another, is unclear to everyone studying this problem. However, particular steps in increasing dryness and climate variability are known to occur from these deep-sea records at 2.8, 1.7, 1.2, and 0.6 million years ago. After 2.8 million years ago, the time when large-scale glaciers first appeared, ice ages have not existed on Earth forever, although there were some doozers in the past, which we'll talk about in a few lectures. Only in the last 2.8 million years have glaciers come and gone with regularity on Earth. That period, 2.8 million years ago, is a particular marker in the evolution of the fossil record of the human line. It's when Lucy, the lineage that led to Lucy, the famous skeleton discovered in Ethiopia some decades ago, split into two separate species. At 1.7 million years ago, another step in climate change, drier climates predominated in Africa, and the large-brained Homo erectus species first appeared. At 1 million years ago, as the dry-wet climate cycles intensified, the genus Paranthropus died out, leaving Homo as the sole surviving genus in the hominid line. Now, one camp suggests that it's the change in climate that pushed human evolution along, and another suggests that it's the increased variability, not the change from wet to dry, but the fact that wet to dry cycles were coming with greater rapidity pushed human evolution, driving us to require better adaptability for the species to survive, where better adaptability presumably leads to larger brains and perhaps to language. Now, while this theory is somewhat controversial, the correlation between changing climate and human evolution provides yet another tantalizing connection between our physical and biological evolution on the planet. As we reach back several million years, another major factor must be taken into account in discussing the history of Earth's climate, and that's the positions of the continents. Indeed, the climate system shift about 3 to 4 million years ago, which led to the onset of the ice ages, may well have been linked to the last major event in the ever-changing positions of the continents on the surface of the Earth, that being the closing of the Isthmus of Panama. Prior to that time, the ocean flowed freely from the Atlantic to the Pacific between North and South America. However, as part of the ongoing motion of the floating continental plates over the surface of the Earth, this region closed about 3 million years ago. This produced a major change in ocean currents, which is clearly seen in the delta 13C ratio of deep ocean forems. Unlike the forems that float on the surface and record the surface temperature very accurately, there are some that live very deep down in the ocean and absorb, as all creatures do, carbon from their environment. A change in the amount of carbon-13 to carbon-12 in these shells indicates a change in the ocean circulation, because that carbon is mixed into the ocean by the currents that interact with the air on the surface and then drag it down to the deep ocean. There's a tight coupling between the ocean and the atmosphere. The closing of the Isthmus of Panama also set up a salinity difference, the amount of salt dissolved in the water, between the Atlantic and the Pacific Ocean, which, as I mentioned earlier, is responsible for the great conveyor belt that drives the ocean flows today. There was no more ability for ocean water to mix from the Pacific to the Atlantic. What happens is the trade winds, the winds near the equator of the Earth, which blow from east to west, evaporate lots of water from the Caribbean Ocean, Caribbean Sea, carry it over Central America, and dump it in the Pacific. Well, when you evaporate water, you evaporate the water, not the salt. The salt stays behind. And so the water gets evaporated, carrying it to the Pacific, dumping fresh water into the Pacific, removing fresh water from the Atlantic, leading to a difference in the salt content of the two oceans. Indeed, the current distribution of all the mountains of the world, the huge range of mountains that runs all the way from Alaska down through California, and then the Andes, which run all down South America, take the dominant winds in mid-latitudes, which flow from west to east, and block the water vapor they're carrying, having it dump in the Sierras and the Andes and flow back into the Pacific Ocean. Whereas the water that's evaporated from the Atlantic gets carried over all of Europe into Siberia and eventually falls and flows off to the Arctic, again removing fresh water from the Atlantic and dumping fresh water into the Pacific. This ultimately leads to a difference of salt content of about 1 part per thousand between the Atlantic and the Pacific. This may not sound like much, but it's enough to play a dominant role in driving the entire ocean circulation. This huge river that starts in the ocean in the Caribbean and flows north in the Gulf Stream carries as much water as 100 Amazon rivers. It carries its warm, salty water north, cools. Because it's salty, it's dense, sinks to the bottom of the ocean, and redistributes this throughout the world. It has recently been suggested that climate is more stable during interglacial periods than in glacial states, owing to the salt difference that's kept up here. Ocean cores have allowed us to extend Earth history to millions of years. Most of the changes we see take place on timescales long compared to human lifetimes. Indeed, the dominant philosophical underpinning of Earth history since the middle of the 19th century has been uniformitarianism, the slow accumulation of changes over very long periods of time. The Colorado River slowly carves out the Grand Canyon over millions of years. The Himalayas rise as India collides with the Eurasian plate. The majestic glaciers expand and then contract on timescales of hundreds of thousands of years. While this picture is largely correct, sudden and catastrophic changes have also left their mark on Earth's history, and in particularly on the history of life. To understand this, then, we cannot consider only changes on the Earth itself or changes in its energy source, the sun. By considering the small tugs on Earth's orbit that the moon and the planets produce, we have acknowledged that the Earth and the sun are not alone in space. While these massive bodies, distant planets, produce subtle changes in our orbit that affect climate on long timescales, much smaller bodies in space can have an even larger and more immediate impact on Earth. Our story next time presents the most famous example of catastrophic intervention, which occurred 65 million years ago and led to the death of the dinosaurs.